Section 1.3 covers predicate logic. Recall, a statement is a declarative sentence that is either true or false, but not both. And we discussed earlier how a sentence involving a variable is not a statement. So, a predicate is a declarative sentence whose true-false values depend on one or more variables. And we use function notation to represent a predicate. For example, we can define the predicate P of x by the sentence x is even. And we can define a predicate with two variables. The predicate Q of xy is defined by the statement x is heavier than y. So whatever we put in the place of x would go first in this sentence, and whatever we put in the place of y would go second in this sentence. When you substitute specific values for the variables, the predicate becomes a statement. So if we substituted a 2 into the predicate P, we would have the sentence 2 is even. That sentence is always true, so P of 2 is a true statement. We could substitute feather and brick into the predicate Q, in which case we would have the sentence, a feather is heavier than a brick. But a feather is not heavier than a brick, so Q of feather brick is a false statement. When defining a predicate, you must also define the domain of values that the variables can take. For example, with the predicate P of x defined by the sentence x is even, the domain could be something like the integers. But for Q of xy, x is heavier than y, the domain would have to be some collection of physical objects that we could weigh to decide if one was heavier than the other. A quantifier modifies the predicate by describing whether some or all elements of the domain satisfy the predicate. And we only need two quantifiers. We'll need one called the universal quantifier that translates to the phrase for all, and it's denoted by this upside down capital A. And we also have the existential quantifier, translates to there exists, and it's denoted by this backwards capital E. So when you see these quantifiers, the for all symbol would say all elements of the domain satisfy the predicate. And when you see the backwards capital E, that would imply that some elements of the domain satisfy the predicate. When we put a quantifier in front of a predicate, we form a quantified statement. And just like all other statements, that quantified statement is either true or false. So for example, if we let the domain be all real numbers and take P of x to be the sentence x times 0 equals 0. Consider the quantified statement for all x, P of x. So in English, that would translate to for all real numbers x, because our domain was all real numbers. So for all real numbers x, x times 0 equals 0. We know that to be a true statement. We know that if we take a real number and multiply by 0, we get 0. So the predicate became a statement with this quantifier. Now let's let the domain still be all real numbers, and we'll take the predicate P of x to be the sentence x squared minus 5x plus 6 equals 0. And q of x will define to be the sentence x is negative. Now recall from algebra that x squared minus 5x plus 6 factors, and when we try to factor a quadratic, we're looking for two numbers that multiply to be the constant. So in this case, we want to multiply to be positive 6, and you want to add to be the middle term. So we want to add to be negative 5. And the two numbers that accomplish this, multiply to be positive 6 and add to be negative 5, are the numbers negative 2 and negative 3. So if we set each of these factors equal to 0, we would get two solutions. We would get either x equals 2 or x equals 3. So we want to determine, is the quantified statement, there exists x, such that p of x and q of x, we want to decide if that quantified statement is true or false. So first we need to figure out what this quantified statement says in English. So what we're saying here is that there exists some real number x such that p of x and q of x, so such that x squared minus 5x plus 6 equals 0 and x is negative. Well, we showed on the previous slide that x squared minus 5x plus 6 equals 0 has two solutions, x equals 2 and x equals 3. And neither of those numbers is negative, so this quantified statement is false. The most important thing you need to be able to do with predicate logic is to write down the negation of a quantified statement. So for example, let's let the domain be all people and let L of x be the predicate x is a liar. If we consider the quantified statement for all x L of x, that translates to all people are liars. Now, how could we show this statement is false? So we're trying to show all people are liars is false. That means we need to find someone who is not a liar. In other words, we need to show there exists a person who is not a liar. So in symbols, that would translate to there exists x, there exists a person, such that not L of x, who is not a liar. In symbols, universal negation is written when you want to negate the quantified statement of the form for all x p of x. It is logically equivalent to the quantified statement there exists x such that not p of x. So this negation symbol negates the quantifier, so that for all x becomes there exists x, and the negation also distributes to the predicate. So both things change when you negate the quantified statement. Let's stick with the same predicate, x is a liar, in the domain of all people. And this time consider the predicate there exists x, L of x. In English, that would be the sentence there exists a liar. To show this statement is false, we need to show that nobody lies. Or in other words, we need to show that all people are not liars. And in symbols, that would be for all x, not L of x. So in symbols, existential negation is written, the negation of the quantified statement there exists x, p of x, is logically equivalent to for all x, not p of x. Again, the negation symbol negates the quantifier and distributes to the predicate. So there exists switch to for all, and P negates to not P. There are two expressions that come up a lot when we are translating English statements to logic, and knowing the predicate logic for these expressions makes that translation much easier. So the first is a sentence of the form, all blanks are something. So for example, all baseball players are rich. Statements of this form require two predicates. We have one to define X is a baseball player, and we need another one, Q of X, to say X is rich. So in the domain of all people, the translation of the sentence, all baseball players are rich, becomes, for all people, if a person is a baseball player, then they are rich. Because we're not saying all humans are baseball players or all humans are rich. We're saying if someone is a baseball player, then they are rich. And so in symbols, that would look like for all X, P of X implies Q of X. The second common construction would be a sentence of the form, there is a blank that is something. For example, there is a rich baseball player. Statements of this form still require two predicates. So we'll still need one to define the baseball player. X is a baseball player. And we still need Q of X, which is defined by the sentence X is rich. In the domain of all people, this sentence, there is a rich baseball player, translates to there is a person who is a baseball player and rich. Basically, being a baseball player and being rich both define this person. There is a rich baseball player. So in symbols, that looks like there exists X such that P of X and Q of X. So when I see you in class next time, we'll spend at least one class period, maybe two, writing translations between English and predicate logic.